Hello, everybody, and welcome to today's webinar on cloud-native ClickHouse at scale. We'll be talking about using the Altinity Kubernetes Operator for ClickHouse. My name is Robert Hodges, and I put this webinar together. I'll be presenting it today, backed up by a bunch of great people in Altinity engineering. So I'll just jump in and answer a few questions and upfront issues before we go into the webinar itself. This webinar is being recorded, so you don't have to take frantic notes. We will send you a link to the recording within about 24 hours if you signed up for it. You can also go look at it later. We publish them on YouTube. We'll also send you a copy of the slides or link to the slides. So that's as far as recording and slides. Questions, you can use the question and answer box, which is available on Zoom, or you can just post things in the chat. If it seems relevant, I'll just stop or just take it in, along during the presentation. But if it's something that's, off topic or more complicated, I'll probably defer it to the end. So with that, I'd like to jump in. One favor before we get too far in, can somebody confirm both that you can see the screen and that you're getting decent audio? If you can just pop that into the chat box, I would very much appreciate it. While I'm waiting for that, let's go ahead and make a few introductions. So my name is Robert Hodges, and my day job is I'm CEO of Altinity. But I'm basically a database geek. I've been working on databases now for about 40 years. The 30 is a little bit out of date. And it's been everything from pre-relational systems to, of course, ClickHouse. I do a lot of work with Kubernetes. I started working with it about 5 years ago at VMware. And of course, it's a big part of our lives here at Altinity. The other folks who've helped to put this together are the Altinity engineering team. We have a bunch of great people working in the company, database geeks, huge amounts of experience in databases, particularly analytic databases like ClickHouse, but also a great deal of experience in Kubernetes. And in fact, we work constantly with Kubernetes. It is a major part of our product offerings. Our cloud is based on Kubernetes. All of the software we're discussing today is used in our cloud, including the ClickHouse operator. And the ClickHouse operator, of course, we wrote it ourselves. It was first published about 4 years ago, and we've been building on it ever since. So that's the intros. Let's go ahead and dig in. Oh, one final intro. In case there is anybody here who has not worked with ClickHouse before, here's a quick primer. It is basically like MySQL, but it does analytics. So there's even some similarities in the SQL dialect. It speaks SQL. It is open source, of course, Apache 2.0, great license. But then it has a bunch of features that make it a really outstanding real-time analytic database, like the ability to run anywhere. That's also like MySQL. Stores data in columns, very efficient for scanning large amounts of information, incredibly good compression, parallel execution, and all that kind of thing. So ClickHouse will be the subject here, but what we're going to be talking about for the rest of this webinar is how to package ClickHouse and, most importantly, run it on Kubernetes. So let's jump into that. So in the first part of this presentation, I'm going to talk a little bit, give some general background on Kubernetes. What is an operator, and how does ClickHouse fit into all of that stuff? So let's dive in. Kubernetes has been described as a management system or an orchestration system for container-based applications. What does that mean? It means if you use Docker or use some other container system, it means that that Kubernetes will run those for you in various types of environments and do all the things that are necessary to connect your distributed application with the underlying infrastructure that it needs to run. So here's the simplest possible application that you can imagine, which is just running ClickHouse, for example, in a Docker image on a VM somewhere with some attached storage. So if you're just running this, you you probably wouldn't use Kubernetes, but it's a good starting example because it gives us a way of describing and understanding how Kubernetes actually implements an application. So what Kubernetes does as part of this orchestration, container orchestration, is it maps resource definitions to infrastructure. So, and if you haven't used Kubernetes before, or if you're new to it, you'll you'll come in and there's just a bunch of different kinds of resources, things like stateful stats, pods, persistent volume claims. These are basically building blocks for distributed applications. They're not specifically tied to any kind of any kind of infrastructure, but they are necessary. They are there so that you can describe to Kubernetes what is the shape of your distributed application and what kind of resources does it need. So, and in the way that Kubernetes then handles this is that you have these things like a stateful set, for example, that describes a kind of container-based application that needs to have attached storage. A pod more or less correlates to a container. It can actually have one or more containers on it, but it's typically, uh, a, so it's the actual processing. Persistent volume claim is a request for storage, and a persistent volume is the actual patch of storage that was allocated to fulfill that request. And these then map to runtime abstractions, which you'll be very familiar with if you use containers. So for example, the pod maps to one or more containers. The persistent volume maps to a volume. There's, if you go to Docker or other container systems, they use these terms. And then those map through to actual physical infrastructure. So for example, in the end, what runs in a Docker container is just a process running on a host somewhere controlled by C groups. So in other words, given some bounds so that it can't eat all the resources on the host. The volume that you have that is attached to your container could be just a patch of EBS storage running on Amazon. I want to say in this talk, I'll be giving a lot of examples that are based on Amazon because we use that a great deal, but what we're describing here runs perfectly well on virtually any Kubernetes on any cloud. The Amazon examples are just that. They're to give you sort of a be able to map this to something that you may have used recently to make it more understandable. So how does ClickHouse, or excuse me, how did I keep getting ClickHouse and Kubernetes backwards here? How does Kubernetes actually do this mapping? Well, basically the way it runs is there's a control loop running inside Kubernetes, and it looks at the resource definitions, which you can think of as a desired state. And it has and the control loop will look at the desired state. It will then go look at the actual state, and it will decide what needs to be done to actually, what action does it need to take to make those two things match. So it just goes round and round and round. And as the desired state changes, sort of as you give new versions of the definition, Kubernetes will look at each resource and then say, do I see a resource out in the environment? So for example, a patch of storage or a persistent volume. No, I'm going to create it. Do I see a change in that resource definition to make it bigger? Okay, I'm going to go ahead and extend that storage. That's all controlled by this loop that is running inside of Kubernetes and allows it to make these iterative adjustments so that eventually the state of the infrastructure matches what you asked for. Now, that's pretty simple, but the thing is that when we actually run ClickHouse clusters, they are quite a bit more complicated than just a single process that's accessing storage. This is a typical example, and not even a very complicated one, of a ClickHouse installation where we have two shards. So that is to say disjoint subsets of data. They are running on two servers apiece because each of the shards has a replica. Moreover, because we're kind of safety minded, we're going to take those replicas and we're going to spread them across availability zones. So availability zone is something that's known to Kubernetes. It's of course very, very prominent in cloud systems, and it basically means a separate data center. And then on top of that, ClickHouse, in order to function as a as a proper application and to make replication work, it will need Zookeeper. It could, of course, use ClickHouse Keeper. It doesn't really make any difference. But because this is a production system, we'll need 3 copies of that. And for safety purposes, we'll spread those across availability zones as well. This is, even here, looks a little more complicated. Once you start mapping it to Kubernetes and building up using these resources that are very basic building blocks, it becomes much more complicated. So for example, you can see how we have the stateful sets, pods, persistent volume claims, persistent volumes, all these resources that define a ClickHouse server, perhaps with some additional processes to do things like backup or whatever. Mapping to storage, there may be multiple, there may be multiple volumes. You can see how this very quickly runs into dozens, or in some cases, extreme cases, even hundreds of resource definitions that need to be pushed into Kubernetes and then properly managed. So if you just had to, go ahead and do these individual resource definitions yourself, this would not be very helpful. It would be quite difficult to manage. So what happened is that Kubernetes, the Kubernetes community, recognized this several years ago, and they introduced something called an operator. And an operator basically is a custom resource definition. So Kubernetes provides a resource definition for persistent volume. That's a piece of storage, allocated storage. The custom resource definition can be for anything you want. And so we have a custom resource definition that describes a ClickHouse cluster. In order to make that work, you're going to need to have you're going to need to have some kind of controller, if you will, that keeps an eye out for these resource definitions when they get loaded up into Kubernetes or when they change. It looks at them and then it decides what to do inside Kubernetes to make them a reality. So you can think of it as just being a layer above the resources that Kubernetes provides for you yourself. So when you put one in, the operator gets a message that says, hey, a new resource definition has arrived, have a look at it. It will then look at the other resources that are defined in Kubernetes, and if they are absent, it will make new resource definitions. If they are there but not in the right state, it will make changes to make them adjust. And this process is often called reconciliation, where we look at what is the desired state and what's the actual state, and then make changes so that it will happen. So this feature was single-handedly turned, in many ways, was the fundamental thing that made Kubernetes become very, very good for managing data, because databases are kind of complicated. And not only do they have a lot of pieces, they also have processes around them, things like upgrade, things like adding new replicas that are complex and need to be done in a particular order. And the operators give you a way of implementing that, and then have a relatively simple description that that users can give you to say what they want. So what we did then is we took this model. It was when we started working on our ClickHouse operator. It was back in 2018. This operator model was actually fairly new at that time, but we began to work on it. And so the operator, as it stands today, almost 5 years later, is that it is distributed as a container, so as a Docker image. It is Apache 2.0, and you load it into Kubernetes, and then from once it's properly loaded and running, you can go ahead and give it these CRDs, this custom resource definitions. You just run the kubectl command, which is your standard way of sending commands to ClickHouse. It gets passed to the operator, and then the operator will do just this adjustment of reality that goes ahead and sets up the cluster for you. So that's how it works. It's a very versatile model, and we've built, now there are tens of thousands of clusters out in the world that have either been set up or are currently running using this operator. So it's very robust. That's the theory behind it. Let's go ahead and see how to use it. So in this next section, what I'd like to do is show you how to install the operator, do a little teeny bit of setup with Zookeeper, and then go ahead and create a cluster. And we'll do a quick demo to show how it works. So The first thing you do is install the ClickHouse operator from GitHub, and you can do this in a single line. There are other ways to do it, but the simplest thing to do if you've never used the operator before is you simply run this command. What it's doing is it's pulling a YAML file which has a number of things in it. It has a description of the custom resource definition for ClickHouse clusters. It also will pull the image for the operator and install it in the kube system namespace. Namespaces are just divisions. You can think of it as being like folders within the Kubernetes cluster. And that does a few other things like sets up a little service account um, and and some other parameters that are necessary for the operator to run. It's all done in this single command. So you run that, and on my machine, the operator is very small. On my home network, I have this up and running in about 10 seconds. The next thing we want to do if we're going to work with ClickHouse is we want to install Zookeeper. You can also use ClickHouse Keeper. As I said, we're pretty focused on Zookeeper for a variety of reasons, but you can use this. You can also go the other way if you want. And again, there's a relatively simple way to do that. We provide a script or YAML file, which will pop up a dev Zookeeper for you. It's just one node. And here are the commands that you can pull it down, and then basically you'll create a namespace to stick it in, apply that YAML file, and then it's up and running. This has a little skull and bones next to it because if you're running in production, you of course want to have more than one node, because if you're using replicated tables and Zookeeper stops, it's bad. I mean, your ingest stops. But this is for development purposes. These 3 commands will get you up and running. Zookeeper will take a little bit longer. It might take a minute to come up because the image is kind of chubby. And so it gets pulled down, allocate storage, and you're ready to go. At that point, you can define your cluster. And I'm going to walk you through a cluster definition just to show you what the parts are. Don't worry, this code looks kind of bad, but it's really only about between 30 and 40 lines of YAML to create a basic cluster. It's quite simple. So what happens is if you come in, you'll see that, and if you're familiar with Kubernetes, there is this kind field which just says, hey, what sort of resource is this? And then we have various types of configuration. So for example, we have a specification for this, and this includes the layout of the clusters. So I want to have a cluster which has 1 shard and 2 replicas. I also want to have my own definitions for the pods, and you'll see these are very simple, as well as the storage. And then because we're maybe planning to do some replication, we'll need to tell ClickHouse where Zookeeper is located. So that's the sort of header information. Let's now look at the definition of the pods and the storage. So these are done through what are called templates, which means they get applied to every pod that needs them. So pod templates. This is the simplest pod template you can have, and it just says, "Hey, I want to run ClickHouse in a container, and here's where to go find it on Docker Hub, or wherever your container repo is located." So this is Altinity stable. These are the long-term support builds that Altinity does for ClickHouse. You can use any version of ClickHouse you want. So you can go get a container from the ClickHouse repo. You just give the name and the tag. It's as simple as that. And what will happen is when this is processed, it'll just pull it down and run that container. So that's the pod. And then there are what are called the volume claim templates, which define your storage. These are similarly very simple especially in non-production cases. Just a couple things to note here. It's first of all, there's a resource request to say how much we want. In this case, we're asking for 50 gigs. And then there's a thing called a reclaim policy. This is actually an important setting that you will not see. That's actually custom to our operator. It's not a normal Kubernetes property, but basically it just says, hey, if I drop the ClickHouse installation, don't delete my storage. In fact, more strictly, don't delete the volume claim that I've made. And what it does is it protects you. It means that you won't lose your storage if you accidentally delete your cluster, which has happened. So that's it. That's all that we need to do. And with this definition, we can go ahead and actually create a cluster. And this is actually a good time to go do that. By the way, if during this demonstration, it will take a few minutes for things to come up. So if you have questions, feel free to throw them in and we can take a few of them while we're waiting. So right now we're out and looking at a Kubernetes cluster. And if you're familiar with this is a watch command, it's running kubectl get all, which is basically going to show all of the resources in the default namespace. And as you can see, there's nothing running here. This is actually Minikube. It's running on a server in my closet. So nothing there. And then over here, what we have is the log of the operator, which is just something that we can watch. If you get, if something goes wrong, you can go over here, or you're curious what the operator's up to, you can just follow that log. Let's go ahead and actually set up the cluster. So here we are. Let's go to, we'll just have a quick look at dev.yaml. This is our cluster definition. And here it is. It's essentially identical to what we just looked at a few seconds ago. So we're going to go ahead and we're going to apply this file. So we're just going to run it like that. And this, what this will do is load this resource definition into Kubernetes. So when that happens, we can expect a little bit after a second or two, we will expect that ClickHouse begins to do, or excuse me, that the operator begins to do something. And you can already see that what it has done, it is defined an initial stateful set. So this is this definition of a pod that's going to need, or it could be multiple pods that need storage. And so it creates that. Then the pod starts to run, and you can see how one is coming up, the next one is coming up, and so within about 20 seconds, we're going to have a full ClickHouse cluster, one shard and two replicas. Okay, it's done. That's it. So we just created a ClickHouse cluster with two replicas. Moreover, there are load balancing services here. So there's a load balancer which we can connect to, and this will load balance us across these two replicas. So if we connect that way, we also have services. A service means in Kubernetes parlance is a type of resource that allows you to connect to a pod or a group of pods. So we also have services for individual pods. So just like your real ClickHouse, you could go through a load balancer, which is for operations like queries where you don't really care which ClickHouse server you land on, or there may be times when you're doing ingest and you want to know, hey, I'm actually going to the first server or the first replica in a shard, so you can give that name and go to it. That's it. So that's all we had to do to create a cluster. Let's go and change it. So we have this dev.yaml file. Let's go ahead and make a change. And so we'll diff it with the next version of this file. So what we're going to do is we're simply going to add another shard. And we do that simply by changing this parameter, the shards count. And if you recall from the definition we had, or the initial definition, we had a replica count and we had a shards count. Simply by changing this number to 2, we can now load this file, and the operator will make it true. So we go back over, and so the operator we'll see this eventually. It'll get an event delivered to it. So if we wait for, like a few seconds, we should see, first of all, a new stateful set being created, and then we will see the corresponding pods coming up. In fact, let's see what it thinks it's. There we go. There we go. I was going to go over and look at the logs to see what it thought it was doing. It takes a few seconds because it's actually evaluating the cluster and creating a plan. You'll notice, one of the things you'll notice is the operator typically does things one at a time. This is also true when we're upgrading. It will upgrade the pods one at a time. And what that means is if you have a cluster with replicas, we will go ahead, for example, if we need to do an upgrade or make changes, any pod that needs to be changed and restarted, we'll actually let the current queries drain out of it, up to some reasonable period of time, and then we'll go ahead and do the operation. And the idea there is that you can do these operations while your applications are running. So we now have uh, two shards with two replicas. Let's go ahead and do an upgrade. So how do we do that? Let's have a quick look. So this time we've got still yet a third definition of this. So we'll compare it with the one we just applied, which is dev01. Now what we're going to do is we're going to upgrade this simply by changing the name of the image. In fact, let's go ahead and look at that just to give you the full perspective. So here's our new definition. All we did is change this image that you see in the middle of the screen. And now we're going to apply that file and let the operators and see what the operator decides to do with it. So let's go ahead and make a command for that. We'll apply it and off it's going. Let's go have a look here and see if we notice anything happening. Actually, this is a good time to look at the operator. So the operator is chugging along here. We will eventually see some messages that show that it recognizes it needs to do an upgrade and that it's planning to do it. This may take a few minutes, so or a large number of seconds as it thinks through it. So anyway, we can let this go for a while, but it will eventually go ahead, restart all the pods, and then pull down the new images if it doesn't have them already. And excuse me, it will stop the pod. It will stop each pod. It will then respin the pod and attach to storage, but the pod will now have the new version of Kubernetes of ClickHouse. So it's basically as simple as that. And in fact, that's the basic for the actual automation of the upgrade of going between ClickHouse versions. It's really that simple. Let's see if it's actually done anything yet. Nope, it's still thinking about it. It'll get to it presently. And when we come back and look at this, we'll see that these have been updated to a new version. So that's a demo, gives you kind of a sense of what these things are like to work with. What I'd now like to do, this is a very simple example that we're doing here because we're just working with a dev instance, and it has very little. We've made very simple changes, and we're not looking for something that stays up. Oh, here we go. So it's finally starting the upgrade after thinking about it for a bit. You can see how the containers are getting created up, and so this upgrade is well on its way. Let's at this point switch back then to the presentation and go ahead and talk about a couple of other things. So even in these dev environments, it is helpful to, one of the things I always like to do and I recommend this for anybody who hasn't used this before, just make sure your storage got allocated correctly. You can do things like go ahead and the PVCs, the persistent volume claims. If you allocated storage, make sure it really showed up and it's the right type. You can look at the persistent volume claims, so on and so forth. This is just basic sanity checking. If you want to get to one of these to see what it's doing and go in and poke around, you can use the kubectl exec command. That allows you to go straight into the into the running container. And in this case, we're going to jump right in and run a ClickHouse client. If you would like external applications to get hold of it, then you can use what's called port forwarding, where you're telling, in this case, Kubernetes with Minikube, you're telling it, hey, I'd like to have my load balancer exposed on port 8123. And then once you've done that, you can go ahead and, for example, run a curl command and, from somewhere outside, and it will actually, ClickHouse will respond. So this is a simple way of getting an application connecting up. Wonderful question here. Thank you so much. Are there any plans around resharding when adding shards? The idea is to even out data load across volumes, but also query workload on distributed tables across servers. Resharding can be, for example, random or shard key based. Yes, but they're not very far along. So that's the answer. And that is the so the answer is right now the operator does not reshard automatically. What it will do, and this is actually a very powerful capability in its own right, is if you add replicas, it will automatically copy schema to them. So you don't have to, normally when you bring up a replica, you have to go run around and grab the table definitions, but the operator is smart enough to look for things like replicated tables and bring them up in the new replica so that you don't have to put the schema in yourself. Uh, there's a final issue about shards, which is I'll emphasize later on, is that when you take a shard away, the operator does not take care of ensuring that data that is on that shard is saved in any way. So you still have the challenge of having to move stuff around, but the basic operations are fully automated. That bring the shard up, take it away. That part you don't have to do. So thanks for that question. It's really good. Um, Ken, the question about the operator doing one thing at a time. Yes, we do have parallelization um, within the operator. There are certain things that, for example, upgrades, where we tend to do them one at a time just to avoid disrupting clusters. But um, so, for example, one of the things we try to do, and we're working on right now, is to avoid unnecessary restarts because they take time. But for example, it's actually not the parallelization that's a big problem in many upgrades. It's the fact that we wait for uh, uh, queries to drain out so that we don't disrupt so that we don't disrupt operations. That's actually one of the things that makes it go kind of slow. Thanks for the questions. They're great. Um, One other question that comes up, it hasn't happened yet, but we get it a lot, is how do you add a user? That's so I'll just give a quick example of that. There, you can add your own configuration files. You can add a raft of configuration settings. You can change the entry point in the containers. You can add sidecars. There are many things you can do in that definition, but this is a quick one. If you wanted to add a user called root to your clusters and have it enable access management, which means it can run SQL RBAC commands, this is how you would do it. So there's your, hashed password. It's basically the stuff you have in your XML file just expressed as YAML. So that's your basic operation in a dev environment when you're just bringing this stuff up and playing around with it. And let's now turn to actually using the operator in a little bit more serious fashion for a production system. So the first thing you want to do is go ahead and let's pick let's go ahead and pick a Kubernetes to run on. One of the things that we found is that we ourselves use Minikube constantly, and there are other sort of dev or micro-sized Kubernetes. The operator runs perfectly well on them. They're great for dev, but you wouldn't run a production system on Minikube. That would be a really bad idea. Just because well, for example, if you keep Minikube up for 365 days, the self-signed certs expire, and then then everything stops working. So what we do instead is we'll typically, along with many other users of the operator, we'll run, for example, if we're in Amazon, very good managed service for Kubernetes. There's also GKE. There's also Azure Kubernetes Service. DigitalOcean has their own service. These things are great. You can also use Red Hat. So OpenShift, you can use Rancher, you could use Kops. I used to use that a lot before, before cottoning onto EKS. One thing that's important to know is that if you haven't used them before, EKS and GKE are actually very cheap. They have a minimal charge, and I think the same is true of Azure. They have a minimal charge to run them. Mostly what you're paying for is the underlying infrastructure, the VMs, the storage, the networking, but you'd pay for that anyway. So these are great. And so managed services, if they're available to you, are definitely a good way to go. So you'll pick that, and then you'll need to set it up. And actually the setup to build these systems or to operate these systems is really pretty simple. There's only about 3 things you've got to do, to get a basic system up. One is you'll need to provision the cluster in the first place. So, whatever tools are available, you could use gcloud on Google, EKS-CTL over on Amazon, whatever's available to you. You set it up, and then you'll have, uh, in the managed systems, there's a master node, but you can't see it. You'll see the worker nodes. The next thing you'll need to do, speaking of nodes, is for production systems, you'll probably want to have some form of auto scaling. We typically do this, so you can use node groups. You can use uh, uh, yikes. Here we go. Carpenter, having a senior moment there. So something that basically, and we'll talk a little bit about how this works, but the basic idea is that if you provision a cluster, you want to have VMs spin up automatically when they're needed and then go away when they're no longer needed. The final thing is you'll want to be able to manage block storage. So the you can actually run clusters on anything you want. So you can use NVMe SSD, local, in other words, sort of local SSD. That works perfectly well. You'll want to be a little bit careful about that, because if for some reason you can't schedule on the node where your storage is located, you won't be able to use that node anymore and you'll lose your data. We normally use block storage because it turns out that, at least in Amazon and GKE environments, it's for most purposes just as fast as local SSD. There are technical reasons for this having to do with storage bandwidth on VMs. But the other thing that's really great about it is it allows you to scale your compute up and down, because you can go to larger VMs, and what happens, or smaller VMs, what happens is you just respin the VM, reattach the block storage, and all of a sudden you have a different compute capacity attached to it. So it's very good for scaling. So what we would normally do, again, using EKS as an example, we could set something up with Carpenter. Carpenter is relatively simple to set up. It does have the slight disadvantage compared to node groups that you need to know a little bit more about what it's doing to debug it. That's been our experience. We like it because we use it a lot. But that will basically be watching Kubernetes for pod resource requests. And when it sees, hey, there's stuff that can't be scheduled, or there's somebody who needs a specific, can't be scheduled because they need a specific VM type, it'll go make it for you. So it does that adjustment. And then the storage class or storage classes then create, when they see persistent volume claims, they will create persistent volumes to match them. So this, in modern Kubernetes, is a little bit of jumping around that's required. You'll need to, like if you're using Kubernetes 1, 2, 3 or greater, you're going to have to add a CSI driver. But it's, again, fairly straightforward to do. And as long as you have it set up correctly, it works very well. So with this setup, we can actually now do something really important. Is it possible to reuse the pod names in another cluster to create another cluster? This one I'll take later because I think there's a little bit more to it than just the question as it's stated. So now what we can do is we can create a server node, or a cluster consisting of servers that may have particular machine types and be in particular regions. That's another really important thing to do. We'd like to make sure these are properly distributed, and we can control the amount of block storage that's attached. How do we do that? Well, first of all, really important topic is placing the pods across availability zones. The way we do that is we define a pod definition that's different for each of the replicas. So previously I had a replica count. I just said 2, and they would just use whatever pod template was there. In this case, now what I do is I give a list and I say, hey, here's your templates. First item in the list, you don't have to name them or anything like that. It's going to use a pod template that's called Zone 2A. The next one is going to use one that's called Zone 2B. So what that means is I've got 2 replicas. The operator can count, and then when it starts the first replica, it'll use the first template, and so on and so forth. You can have as many as you like. So you do that. Then the next thing you have to do is you have to go and actually define those pod templates, and these are a little bit more expansive than what we had in the in the initial example I showed you, because in this case, beyond the, just giving the image type, we're first of all down at the bottom, we're going to ask for a specific zone. So Kubernetes has this really cool feature. It knows about availability zones. They're stored as metadata data labels. And what we can say is this zone command, or this zone tag, if you will, is saying that, hey, these pods, they need to be on a node that has the value that has the zone value of US West 2A. So that means that this server can only run in the US West 2A availability zone. The other thing we've done on the specification for the containers is that we're saying, hey, these guys have to run on a node with M5 large VM type. And if you've used Amazon, that's an instance type. And so again, if this node doesn't exist, the pod won't be able to schedule. And then at that point, Carpenter or the node group implementation will notice it, make one for you, and then your pod will land on it. So that's all we do. Now, there is one other thing here. There's resource requests. You start to have to pay attention to these when you are in, operating in, in these larger environments, production environments. We'll talk about that in just a minute. Final thing is storage. So this is really simple. It doesn't really change very much. One thing you may want to do is if you have multiple storage classes, they will allocate different kinds of storage. So you may want to be explicit about what you want. Like, hey, I want, I'm on GKE, or, on Google, I want PDSSD storage type, or here I'm on Amazon, I want GP2. So you want to be explicit about it. The size is always the same. There's no differences there. So storage is actually pretty simple, even in production environments. So what's kind of cool here is now, we've got this, this cluster allocated, and it's using the right VMs and they're in the right places. One of the things we can do now is we can scale up. We can also scale down, at least with limitations. But let's say we want to go from M5 large to M5X large, and we want to go from 50 to 100 gigs of block storage. What do? Well, it's already running. We just go ahead and, just as I showed you in the demo, we're going to just make some very simple changes. So for example, we'll go into the pod templates and we'll just change the instance type to M5X large. That's all we have to do to make this go float around, sort of detach from wherever it's running and get scheduled on a VM that's the right type. When you do this, it's actually fairly important. It becomes more important as you begin to get into larger instance sizes to go ahead and actually have requests. So resource requests that match the VM type. The reason for this is that the operator does not currently do things like change the memory allocation that ClickHouse thinks it has, and ClickHouse can actually see how much memory is available on the VM. This is just a Docker and other container systems don't hide that. So what it can end up doing is if these resource requests are too small, you can also leave them out, in which case I think they'll default to just using anything that's there. But if you have the resource requests and they're not right, what may happen is that Kubernetes may say, hey, this guy is using too much memory, and then it'll kill it with the killer. So you want to adjust that. And the other thing this does is it basically prevents, without doing a great deal of juggling, it prevents multiple ClickHouse servers from landing on the same, trying to use the overlapping resources on the same node. There's other ways to achieve that separation, but this does it. So basically, though, to scale up, so make these resource limit changes, make the, ask for a different VM type and apply this, and boom, it will scale up automatically. So again, with storage, wrong title here, sorry about that. Storage type we don't change. All you have to do is change the amount of storage, and we will automatically increase it for you. Currently, in fact, in general, with cloud storage, you can increase it, but you cannot take it away. You can't shrink a file system once it's in use. The The operator right now, if you run it, will restart your servers as it allocates more storage, but it is in future we have a fix which will correct that. Speaking of storage, it's really important to pay attention to storage classes. I mentioned the fact that even in a dev environment, you want to check to make sure storage is really allocated. If you have a syntax error, for example, in your YAML, Kubernetes is not good about saying you just said something to me that made no sense. It will just pass it over and pass over it in silence. So so check your storage, and then the storage classes themselves, you want to pay attention to things like, hey, does my storage allow volume expansion? So most like the EBS and the Amazon and GKE storage providers do allow this. So that will be true in the storage classes. Another thing is the default storage class. If this flag is set to true, that means if your definition doesn't specify storage, that's what it's going to get. There's other things in here that you may want to look into more closely, like file system type, so on and so forth. But these are definitely things you want to pay attention to. They don't change much, so once they're right, you don't really have to worry about them. One final thing, how does the operator manage adding replicas? So this is worth looking at in a little bit more detail. So what would happen in this case is that we'll go ahead and when this is, we'll start with one VM, say with one replica. If we're going to two, there's a number of operations. So we'll add the stateful set, and that will cause the provisioner to add a VM. Once that VM is available, we'll then update the cluster metadata, because you think about what happens when you add more nodes. You have to go change configuration files, like the remote servers file, for example, to tell the cluster, hey, there's different, there's more copies of there's more nodes out there that we can talk to in the cluster. So we update the metadata automatically, and then we copy the schema to the new replica. So this is really handy. And then once the schema is there, basically what will happen is that ClickHouse will then, if you have replicated tables defined, we'll go ahead and we don't have to do anything, because ClickHouse replication will just automatically populate the table data. So this process is fairly seamless. And then there are, if you're using distributed tables, there are normally checks to make sure that, like the replica is caught up, that kind of thing. But these are things that you're probably used to from dealing with ClickHouse in general. So safety tips. There are at least three things that you just want to be very careful about because Kubernetes giveth, Kubernetes taketh away. The primary example of something you do not want to do is we installed the operator using this YAML bundle. You do not want to just run delete -f on this, which is the standard way to make resources disappear. You just don't want to do this when you have running clusters. Why is that? Well, the problem is that inside this bundle, there's the custom resource definition. It is global across the entire ClickHouse cluster or Kubernetes cluster. And what will, excuse me, happen is when you take that CRD away, Kubernetes no longer knows how to, what to do with this resource it's got out there. And in fact, if you try and install the operator again, it will go ahead and delete it. This is just Kubernetes behavior. There isn't really, that I know of, a way around it. So you want to be very, very careful about running this command. In fact, when you clean up, you want to delete your clusters first, and then you can go and run this command and clear off the operator and all the custom resource definitions. We talked about the reclaim policy retain on storage. What this does is if you delete your ClickHouse installation, that is to say the custom resource, it won't take your persistent volume claims away. In fact, you'll have to delete them manually. But if you realize, hey, I didn't really mean to delete that, I want it back, you can just add the resource. You can just rerun the file, put the cluster back, and it'll reattach to your storage again automatically. And then finally, shard management, as we've discussed, there isn't automatically rebalancing of shards, either when you add shards or when you take them away. But if you take the shard number, like you're running 2 shards and you make it 1, it will drop the last shard that you created, and it won't save your data. You need to have moved it already before you do that. So, and that's one of the reasons why the operator allows you to connect to specific nodes so that you can go ahead and move things around. So that's sort of the overview. As you go more deeply into this, here are some other things to look at. Okay, first thing we get asked about is external network access. Uh, I don't show this in the examples because it is complicated and different for every single uh, for every single example, or for every single environment. This is the place. Kubernetes is really very portable inside, but the networking is different for every implementation. Uh, we have a bunch of examples of how to do this, and let me just show you it. What you're going to have to do is go look at the operator uh, uh, code, and I'm here. It's all on GitHub. You can pull it. It's all completely open source. We have a kind of a legendary configuration file called 99 ClickHouse installation max.yaml. It gives examples of all the crazy things you can do. But one of the most valuable parts is what I'm showing you right here is the definition of network services, which again are not a non-trivial aspect in Kubernetes in general. The bad news is it's complicated. The good news is you can do almost anything. So in particular, let's just get down to it. You have the thing that controls what load balancer actually gets allocated is this tag. And so, for example, this is saying, hey, I want an internal load balancer, which means it won't put up a public IP on if you're using Amazon, it's just going to use an internal address. So it won't be routable from the outside internet. So you can go look at this file. It gives you examples. Ping us if you need more help, and we'll be happy to do so. So, and yeah, examples of NLB load balancers, stuff like that. So that's a fairly common question. Let's go back and pull this up. Okay, backup. So we use ClickHouse Backup. We run it as a sidecar, but there are other ways to do this. We are working with some of our users to provide procedures. This is sort of work in progress, but there are ways that you can actually take snapshots off EBS volumes, or in the case of GKE, the similar, sort of like PDSSD, whatever block storage you have. So again, that takes specialized configuration that's beyond the scope of this talk, but it's doable. Security, of course, a big issue. You want these things to be just as secure as they are anywhere else. There's a great write-up inside the project now called the Altinity Operator Hardware Guide, or Hardening Guide, that's just went in a couple of days ago. Check it out. It shows you how to handle users, how to pass secrets around, all kinds of good things, how to secure the network. And then finally, monitoring and alerting. If you're running things on Kubernetes, you've got to invest in this stuff. In fact, I put it differently. If you can't afford, if you don't think you can invest in monitoring and alerting, you probably shouldn't use Kubernetes, because the reason is that, and I'll show you an example. This is what our monitoring looks like for Altinity.cloud. And you can see that we're actually have monitoring that's getting pulled off the VMs that are running for on different ClickHouse nodes. The reason this is important is that Kubernetes hides all this stuff, and you can't just SSH, or for a variety of reasons, you can't just SSH in and go look at stuff. And anyway, you've got potentially many nodes, and you need to be able to see quickly what's going on. So this is the type of monitoring. Of course, you want to monitor ClickHouse itself, but then it's also great to have, in fact, essential to have monitoring of the nodes, so that when something goes wrong, you can figure out what's going on without coming in and laying hands on it. This kind of gets into a question. We have many users who are doing this. There's even a service in China that one of the big internet services that's running on the ClickHouse operator. They sometimes so there's a number of large companies using this for their own cloud services. It's great. They give us PRs. But if you don't want to run this yourself, you can just check out Altinity Cloud. We'll run it for you. And one of the things Altinity Cloud can do is if you have a Kubernetes, let's say you're running, GKE, for example, and you want to keep the data locally, what Altinity.cloud can do is a very simple procedure to register, to install this thing called the Altinity connector. It registers with Altinity.cloud, builds a management, bidirectional management channel, and allows us to, basically put up a screen like this, which is doing all your cluster management out of a centralized control plane, but you have the data, you have the code. If you don't like us doing this, you can just disconnect it and your stuff keeps running just as it did in the examples I've shown before. So that's about it. We're going to run a little long, but I'll stick around for questions. Just some summaries on this. So the Kubernetes operator, it manages ClickHouse clusters and I think does a pretty good job. It has over 1,200 stars on GitHub. Its operators are kind of obscure in the grand scheme of things. This is one of the most popular ones. It's certainly the most popular one for anything resembling an analytic database. You can try it out on Minikube or any other dev version of ClickHouse. It takes really a few minutes to set up and try it out. In fact, if you want to just learn ClickHouse, this is one of the best ways to do it because, like if you want to set up sharding and replication as complex configuration, the operator just does it automatically. You can then go in and poke around and see how it did it. Most users we're familiar with are using managed Kubernetes services, and we do it ourselves. But of course, you can use not Redshift. That's a OpenShift, Rancher, Kops. You can use those. If you're running in provisioning, you want to really pay attention to sort of the sort of scaling issues. For example, mapping ClickHouse nodes to VMs, and then taking care of services backups, all that kind of stuff. And there's the docs on the site are the place to go if you need help with that. We have examples of everything, and you can always ask questions, file issues, so on and so forth. Here's more information. I'll scan over that. I just want to put in one more pitch. If you like this, please help us make it better. It is 100% open source. It's Apache licensed. So write blogs about it, tell people about it, log issues. If you find problems, tell us what they are. We test the daylights out of this for the use cases that we have, which are running our cloud. So as long as it's something that we're doing, it's probably, but the code paths are pretty well exercised. But if you do something different and or that we haven't thought of, you'll find things we haven't found. And then finally, if you find something or you see something that the operator is not handling, send us a PR. We love them. We've taken a bunch of them. As I say, there's at least one, probably two cloud services that are using this. And these are sort of ClickHouse services. They send us PRs. It's great. We love having contributors. So that's it. There are let me just make sure that I think we had a couple questions coming up. Let's go have a look at them. Yeah, coming back to so a question again from Andre. Are there plans on resharding functionality for the operator? And my answer is the same as it was earlier in the talk. It's a work in progress. We're very interested in this topic, but I can't give you a date when the operator is going to handle this. If it is something that that interests you and you'd like to help, give us a call. It's a very, very important topic for ClickHouse as a whole, and particularly, but well, obviously in this environment. But this is just the reason we don't have it is that ClickHouse itself does not make it simple. So, for example, doing something like what Cassandra does, ClickHouse doesn't do this yet, and but there is work afoot to do it. Right now, it's fairly straightforward to do manual resharding. They're increasingly good commands to move parts, for example, but it is still a process that you have to drive yourself. So sorry for the non-answer, but yep, if you want to see it happen, come contact us and help us get it done. We'll do it eventually, but you may get it faster if you help. Question here, is it possible to reuse the pod names in another cluster to create another cluster? Oh, okay, now I understand this. Yeah, I think the answer to this question is going to be no. In the notion, can I somehow, you know, repeat the pod names and have my data transferred over there automatically? The answer to that is no. If assuming I'm understanding the question, you basically, the simplest way to create a new cluster, and the way we do it in our cloud, is we use ClickHouse Backup to back it up, say to S3 or to whatever, or to a local file system, and then we restore it into it. Then we make a new cluster and restore the data into it. That's the simplest way to do it. It's really, that can be, we have that highly automated, so it's actually a pretty easy procedure to follow. And I highly recommend doing that, especially if you're doing like an upgrade and you want to know how it's going to work. Do a backup of your existing data, bring it up in a new cluster. The cool thing about Kubernetes, of course, is you can, as I've shown, you can bring that cluster up really easily. All you have to do is change the cluster name and everything else will just work. Um, and then restore from backup, run your upgrade, make sure it's good. And then once you're happy, you can throw that cluster away and go do the upgrade on the real one. Let's see. I see, will there be a recording shared after the meeting? Yes, absolutely. You should get it within about 24 hours. You'll get a link to the slides and a link to the recording. And I think we're at the end of the questions. Let me just say, I thank you so much for attending this. It's been a pleasure presenting it. Come check this, check out the Altinity Operator for ClickHouse. If you have questions, come talk to us. We run Altinity at Cloud. We do consulting. And, if you think you're really good at this and like it, we are hiring. In fact, we're looking for a Golang programmer today who can work on exactly this stuff. So there's also that. With that, since I think we've got the questions covered, I'd like to thank you all very much. I'd also like to thank the Altinity engineering team who, worked on this for years at this point and have generated a lot of the information that I've shared with you today. So thank you, and thank you all, and have a great day. Talk to you soon.